Hello and welcome. We are going to do experiment number 8, half-life lab. Half-life is defined as the time required for half the original amount of a substance to undergo a chemical reaction or a change. This particular reaction, such half-life can be calculated for first-order, second-order reactions. And for a first-order reaction, the half-life is calculated as ln Nt over N0 is equal to minus Kt, where Nt is the number of atoms or concentration at a time t, and N0 is the original concentration, and K is the specific rate of the reaction. The negative sign indicates that as the reaction proceeds, the concentration of the reactant decreases. This is a very useful tool to determine the radioactive isotope half-life because it can give you a lot of information and how to treat exposure to such kind of radioactive isotopes, and is a characteristic of each isotope that is there. This same expression, first order expression, can be calculated or written as Nt in an exponential form as Nt is equal to N0 e raised to the power negative lambda t, where Nt is the time, number of counts or concentration at time t, N0 is the initial concentration, lambda is the specific rate of the reaction. The negative sign indicates that the concentration decreases with time. Now, if Nt, the concentration at any given time, is half the original amount, then we can write this particular expression as N0 over 2 is equal to N0 e raised to negative lambda by t. Or we can write this as, taking the logs, you will find that ln 0.5 is equal to negative lambda t. The log of ln 0.5 equals 0.693, and this is equal to negative lambda t. Therefore, the time for half a life is calculated as 0.693 divided by lambda. With this, I'm going to share my screen with you so that we can do the experiment and complete it. So starting, go to the file, open a new thing, select the half-life lab, open it, and all the description that I have said in the introduction for this particular lab in my own words is also repeated again under the introduction. And when you write the introduction, do make sure that you write it in your own words. After that, we go to the procedure. The procedure is twofold. The first one is to measure the background radiation using a Geiger counter. Take the average of the readings for 5 sets of readings, take the average and keep that as the average background radiation, which must be corrected as everybody is exposed to the universal background radiation all the time. Second part of the experiment consists of measuring the half-life, in which again we select the Geiger counter, open the setting dialog box, set the counter using clicking the right counter, we get the menu, and use that same menu to set the source as thallium 207 at 2 centimeters from, you set the position at 2 centimeters for the source from the Geiger counter, and then set the shielding to none, and then go on taking the readings from 0 minutes to 6 minutes or 360 seconds. How to perform that experiment, I'm going to show you now. You go to select the Geiger counter with its track, and when you get there, you see the source is none, the source position is 1, shield is none, and say okay. And there you get the track. As you can see, the CPM counts on the Geiger counter is going on changing. So go to the observation, put in 5 measurements, take the average and divide it by 5 and record it. Then we go to the experiment itself, go to the setting. Here is the dialog box. Now you select the source as thallium 207. You put the position as 2, and then there is no shield at this point in time. So, and then as soon as you start, now you record what is the reading showing on the counter. Write it down as 0 count, and then click on the timer and start. Then as the timer moves, it's going to move very fast. So when it comes to 30 seconds, as you can see, it's moving very fast. So keep an eye on that particular timer. When it comes to 30 seconds, record the 30-second reading while the timer still proceeds on. So now the times in seconds is 24 seconds, 25, 26, 27, 28, 29, 30, and it's 4525. So you write it down over here, 4525, and then continue for the next. At 60 seconds, you can take another reading and write it down. So get the 0 count, write the 1 for 30 seconds, and I'm repeating it for 60 seconds so you can get the answer. 960 4322 4322. So 4322. Now in this way you fill up this chart table, and then what you have to do is get a corrected count. Corrected count implies that whatever the count you got, subtract the background and you will get the counts. So now you have the counts as well as the time. And so when you plot a graph, you can plot it ln corrected count versus the time. So the count goes on the y-axis, the time goes on the x-axis. Any two values you take, then you can subtract it, get the logs, subtract it, and then the time, difference in time you record. And so the ln divided by time will give you the lambda for the reaction. And that is there. Once you get the lambda, then 0.693 divided by lambda will give you the T1/2. So now you will have two methods to get your results. First is to look at the original, corrected original background at 0 time and check at what spot will you get exactly half the amount. Record that time, and that is an approximate time because you cannot calculate it correctly. Record it. Next, from the graph, see what would be the time, because you know the expression 0.693 divided by lambda will give you your T1/2. Use that, so write down from graph, this is the T1/2. Then include those numbers in your result, and then use those results to calculate or determine, explain the discussion for this particular experiment, as well as the conclusion. Make sure that you complete the template for this particular lab and the homework itself. And once it is completed, submit it in the correct box. And with that, I'm going to stop my share as the experiment is over.